Log on, tune in, find out. Another good idea from Cambridge.
To announce another new lecturer for our course here, Liliana Borcea from Rice University, and she has worked for years on random media and several other topics, and I printed the CV. It's quite impressive, so you might have a look at some point, but we don't want to go into too many details here as we did before. So it's a pleasure to listen to your introduction to random media.
Thank you. Okay, so I will talk about imaging, array imaging in random media. Like it was mentioned already, I've been working in this area for a while now, and here are my main collaborators. So George Papanicolaou and Crisula Tsonka, they have been working with me in this area for since the beginning, and also with Jocelyn Garnier, we have some recent results that are actually included in these talks. So basically, what I'm talking about is an inverse problem for the wave equation, which is shown here. And essentially, so everything I will discuss here applies to waves in unbounded media. Okay, so I'm going to completely neglect boundaries. Now, if you have boundaries in these problems, especially in the case of sort of highly scattering media or random media, those boundaries can significantly change the problem. So for example, it has been shown recently that if you consider wave propagation in media that are layered, okay, finely layered media, and then if you consider, let's say, a boundary, so suppose that the layered medium lies in a half space, and then you have a boundary which is perfectly reflecting, so like a sort of sound soft boundary condition, as it was mentioned here before, then it turns out that that boundary completely changes the problem, because the waves, as they go in the medium, they are going to be constantly scattered back, and then they are going to be scattered back from the boundary, so it creates sort of like a waveguide effect, okay? And so boundaries in this business can change the problem radically, and for example, last year in MSRI, I talked about imaging in random waveguides, so that's a completely different topic. So here, I'm going to concentrate in the case of unbounded media, and I'm going to talk about essentially two problems. So the first one is the one of is an inverse problem for the source. That is a problem that was that was discussed in great detail by Gunther Ullmann, for example. So the inverse problem for the source is to determine the source, which is the right-hand side here. Okay. So I'm going to talk about that problem too, but but there will be quite a different discussion than what Gunther gave. So first of all, we will not be concerned here with inverse methods methods that give a quantitative estimate of this source. Okay, so we will look at imaging methods that sort of give us an estimate of the support of this source. So that's one simplification that I will make. And then, of course, what I really want to concentrate on is the case where the medium through which the waves propagate, so that is this wave speed here, is going to have rapid fluctuations. These rapid fluctuations are due to inhomogeneities in the medium. Okay, so these inhomogeneities in the medium is what we are going to model eventually with random processes. And so the goal of my talk is to understand, to explain how these inhomogeneities affect the inverse problem and what can we do to take care of that. Okay, so the focus is rather different, but really I'm talking about a problem that is related to what Gunther described. Okay, so that's the inverse source problem. And then there is also the scattering problem. So what is the scattering problem in this context? So there will be, in what I discuss here, there will be all sorts of there will be a lot of scattering, right? So there will be scattering from many inhomogeneities in the medium. It turns out that given the kinds of data that one has in practice, it is impossible to image, to determine these inhomogeneities, okay? So So what we really mean when we talk about the inverse scattering problem is we are looking for sort of loci of strong jump discontinuities. So for example, you can in the Earth, so this is a problem that arises in the Earth. If you make measurements of the wave speed in the Earth, then you will find that it is a function that varies rapidly. So it's going to look like that. Okay, so there is fine layering. So there will be a lot of scattering from this. Now, how much scattering it is, it depends on what is the wavelength of the waves that you send through and what is the scale of this fluctuation. So what do we really mean by imaging scatterers? Where once in a while there will be some strong jumps. Okay, so there will be fault lines or something. So the reflection from such a jump is going to be much stronger than reflection from each of these inhomogeneities. Okay, and we are really interested in imaging these jumps, not this stuff. All right, so that's the difference. So, okay, so now since I divided the problem in inverse source problem and the scattering problem, so we're talking about imaging with arrays of sensors. So here is a sketch. So in this business, people call this, so if you look at the inverse source problem, then the arrays of sensors are called passive. And this name comes from the fact that the sensors in the array, all they do is receive signals. Okay, so in the inverse source problem, you have some source over here, and that emits some signal, and then you have the sensors that are far away, and they are going to receive to measure the wave field. Okay, so now let me describe a little bit the problem. So, like I said, so I'm not really looking. So you see, I already idealized this source. So I'm going to look in this talk at a very special type of source functions, which are these ones. So they correspond to an idealized source at a point, which is at point y star. So that is what we will try to determine. And this source is going to emit a signal, which is called here f of t. Okay? So why will I look at such things? Well, typically, when you have an imaging method, what you want to understand, the first thing when we analyze that method, is how it focuses, what is the resolution. And the way to do that is to look at what is called the point spread function. Okay, so if you have a source like this one, which is delta function, which is a delta distribution, so you have a source that is highly localized over here, then you will have an imaging function. That imaging function is going to give you an estimate that is going to be not just this point, but is going to be spread out around it. And then, so the resulting imaging function is what is called a point spread function. And you want to understand that. You want to analyze that. You want to understand what is the resolution, what is the spread around the point that you want to estimate. Okay. So I'm going to look at these kinds of source functions. Now, let me talk a little bit about the array of sensors. What is this array of sensors? So I'm talking here about acoustic waves. So the sensors will be transducers. And what I mean by an array is that we have a collection of transducers. So of course, in real life, there will be just a sort of a discrete set of transducers like this. And the reason we call this an array is because the transducers are going to be sort of close enough together such that if we look at them from far away, they will behave as a collective thing, which is what we call the array. And in fact, you'll see that mathematically, we are going to approximate this discrete collection of the sensors by a continuum aperture. Okay? Now, this is opposed to what is called a problem with distributed sensors. So that would correspond to the case where you have one sensor here, another one far away, and so on. So that is a very different problem, and the imaging techniques are quite different. Okay? So that's what we call array. Now, let me also mention another thing. So what is the data? So the data consists of measurements of P. So P stands for acoustic pressure. Now, this P is the solution of this equation for the given source that you want to determine, okay? And what you do is you measure this pressure field at the locations XR. R stands for receiver here. So you measure this pressure field at the location of the receivers in the array. And you make these measurements over the time t, which is some time that begins right after you emit the signal from the source, and it goes up to some time capital T. Okay? So now, if you remember, in Gunter's talks, there was mention about how long you measure, right? So there was an issue about having an infinite time window or not. So here, you will see that, in fact, yes, we are going to make the approximation, essentially. So even though in real life there is a finite time window, it is quite convenient mathematically to assume an infinite time window. So why is it reasonable to do that? Well, usually in these problems, what the source emits is a pulse, okay? So this signal f of t is what we call a pulse. So pulse is just some sort of a short signal. And the idea is that, you know, this is going to travel to the medium, and so when it reaches here, you are going to observe something around the travel time that it takes to go from here there, okay? And after that, you can measure for a long time after that. Nothing is going to come. That's the idea, right? So then, because we are dealing with short pulses, we often in this business make the approximation of infinite time windows. Of course, when you have a scattering medium, that's not quite right, so that's really an approximation. Okay, so now the pulse. So the pulse, I describe it here. This is how typically it's introduced. So the pulse f of t is determined in terms of this function fb, which is called the baseband pulse. And this baseband pulse is a function that has a support in time that is of order 1 over b. Or if you go in the frequency domain, so if you write the Fourier transform of the pulse, f of omega, then you have that is given to is given by the Fourier transform of this baseband pulse. Now this omega 0 here is what is called the central frequency. So that just tells us where in the frequency domain, okay, so this is the frequency, so it tells us where in the frequency domain is going to be centered the support of our pulse, and then this baseband pulse FB is supposed to have a support of order B. So, or sometimes, so it should be B over 2 here, so you have that omega minus omega 0 should, B over 2 plus omega 0. Omega 0 minus B over 2. So the length of this frequency interval is B, and this B is known as the bandwidth. Okay? So when you go in the time domain, when you do a Fourier transform of such a signal, so you go back in the time domain, then you are going to find that FB of t has a support which is like 1 over B. Okay? So we are talking about short pulses. That means that we have broad bands, so B is large. Okay. So this is the setup for imaging with passive arrays, and this is now the setup for imaging with active arrays. So now the arrays are called active because we are looking for reflectors in the medium, and now the excitation comes from the array itself. So now the transducers in the array are going to be both sources and receivers. So that's why the array is called active. And so the data, the array data now is going to correspond to the pressure field P that is received at receiver XR. So this will be, for example, a receiver. that is due to an excitation from a source, which is another element in that. And we can have as many sources as there are receivers, or fewer than that, or whatever. And then again, the recording is really over a finite time window, but we are going to idealize that to be an infinite time window. And again, in this talk, I'm going to assume that I'm looking for a point reflector, because I'm going to look at the point spread function. Okay, so now the imaging methods, so one imaging method that I'm going to introduce here, it's a widely used method in fields such as radar, seismic imaging, and so on. It's known as a migration method. And to motivate that method, it's useful to look at the problem, at the inverse problem, as a least squares data fit problem. Okay, so the simplest way you can imagine to formulate this inverse problem. So let's look, so here on this slide, I'm talking about the scattering problem. Okay, so I'm looking for jump discontinuities essentially in the wave speed. And so a natural way to formulate this problem will be to try to find the wave speed c that gives us the best fit with the data d that we measure. So the data d will be the pressure field that we measure at the array as I just described. And so we want to fit that with this, where f is the forward map. So the forward map is the map that takes the wave speed and maps it to our model of the data, which will be the solution of the wave equation, right, for this model speed. Okay, so now the reason, so this is never done in practice, at least in the applications that I described here. And so in the late 80s, early 90s, there have been papers, so for example, Guy Chavon, Patrick Lally, so these are papers that have been written mostly with the application of sort of geophysics imaging in mind, but they are very nice mathematical papers. So they have shown very carefully with analysis and numerical simulations that solving this problem is impossible. So what really happens is that if you look at the objective function, which is this function here, well, this function is a bad function in the sense that it has many, many minima. So if you want to solve this problem with any optimization method, you are going to fail. And there are various reasons for that. So, for example, Bill Symes has very nice papers written about that, and apparently the fault, so there are two big issues. The first one is that one does not have access to the whole frequency spectrum, and the other one has to do with the geometry, with the fact that you only measure at an array that is far away from the stuff that you want to find. So really, it's the sort of the data gathering geometry that creates also a problem. So this is impossible to do, and because of that, what is usually done is one simplifies the problem by essentially breaking it into two parts. Okay, so what one usually does is it says, okay, well, I can really write the wave speed like this. So I can write it in this form, and what this says is the following. So it says, okay, well, my medium consists of a background with wave speed v, okay, and then you have the reflectivity. So this is the function that models these jumps, which is what I want to determine, right? So this is the stuff that creates these strong reflections, and this is the function whose support I want to find, okay? And the idea here is that, so really this is done with the following idea in mind. So one thinks of this function v as being smooth, okay? So what that means, so smooth means that the waves are going to go, they are not going to be scattered, right? So, and this function v is what you may think, it's what determines the so-called kinematics of the data. So that tells you how, the waves propagate, what is the travel time, and so on. So that's what one usually thinks about. Of course, in our context, that's not going to be quite right. We will see that in a moment. And then this rho is the part that gives you the dynamics of the data. So that is the part that gives the wave scattering. Okay. So one divides the problem into two problems. So the first one is velocity estimation, which is the problem of finding v. And then the second one is the scattering problem, which is the one of finding rho. Okay, so these two problems turned out to be quite different. This problem turns out to be much easier than that problem, right? So finding the velocity is a hard problem. And well, so Gunther did a lot of work on that, so he will tell you more about it if you want to know. So there is sort of like travel time tomography or all kinds of methods that deal with that. But this is a very, very hard problem. Now the problem of finding the reflectivity, depending on what the setup, it could be simpler or harder. But the point is that the methods that try to find this are very different than the methods that try to find that. Okay? And so in principle, so the class of methods that I'm going to describe here is the so-called imaging methods. There will be methods. Yeah, well, I'll get to that in just a second. Okay, so now the problem is to try to find this rho. So what we do, okay, maybe I shouldn't. So what we are actually going to do to find this reflectivity is we are going to make an approximation, okay? So we are going to do a linearization or like the Born approximation. That's what is usually done at least in the community that I talk about. And Andreas, you talk about the Born approximation. So that's going to be easy. So what we do is, so we write so we write this in this form. Okay, so we make a linearization, and what this means is the following. Okay, so you have the wave equation, which I'm going to rewrite now in this form. Okay, so this is the wave equation, which I rewrote like this. And now I wrote the solution of this equation as P plus delta P. Now this P is the solution of the wave equation without any reflectivity in it. Okay? And then, so the linearization, the Born approximation, amounts to writing an equation for delta P, which is the perturbation of the solution induced by the reflectivity, like that. So that is essentially what you do in the Born approximation. And what we mean by, so what we mean by this operator, this linear operator df, so this is the operator that takes reflectivity functions to the data space. So this is going to be a function of time, the receiver location, and the source location. And this is simply the solution of this equation, of this linear equation. Okay? And I wrote explicitly what this is here on the slide. Okay? So this is very easy to see. So so now first of all, let me explain so you will see that, you know, even though I'm talking about problems in the time domain, I'm always going to write things in the frequency domain. And the reason is very simple, right? Because, so in this case, f is the pulse okay, so I have a point source at the I have a point source that emits a pulse, right? So now the pressure field P, which is what appears here on the right hand side, is given by the pulse convolved in time with the solution of the equation with just this delta with the delta function. So that's the Green's function, right? Is the pulse convolved with the Green's function. So convolutions are kind of awkward to deal with, and the best, you know, the nicest way to deal with them is to go to the frequency domain where convolutions become, you know, products, and that's really one of the reasons why we always talk about things in the frequency domain. So this is the expression of this linear map. So what this says is exactly what you see here. So when you go to the frequency domain, when you take the Fourier transform because of the second time derivative, you have the omega squared here. So that's omega squared divided by v. That's the factor that comes by v squared. That is the factor that comes from here. Then you have the reflectivity. And then you have the solution of this equation, okay, with the right-hand side. Now the right-hand side is what? Is the pulse, f, times the Green's function, which is the Green's function that takes you from the source to the point y where you have the scattering. So that's this p, the Fourier transform of p. Okay? And then, of course, so that's, and then you have the other Green's function that takes you from the point where you have the scattering to the point where you measure. Okay? So this is rather simple. Okay, so this is the Born approximation, and then the optimization problem that we want to solve now is sort of simple linear least squares, and it says minimize over the reflectivities the objective function that gives the best fit between this, what this linear mapping gives, and the data. Now the data is this one. So it's d minus f of v squared. So you can think of this data as being what you measure minus the first arrival. So let me explain that. Okay, so you have a source, you have a receiver. Okay, the source emits a pulse, and then the receiver is going to measure what comes. Okay, now what should come? Well, if there is no reflectivity in the medium, then the only thing that the receiver is going to see is what we call the direct arrival, which is the signal that travels from here over here, right? So it goes like this. So that's the direct arrival. So that is what is modeled by f of v, right? And then, now of course, if there is reflectivity, then the pulse is going to travel to the medium, is going to scatter there, and is going to come back. Okay, so we are not interested in the first arrival, so that's why we subtract it. Okay, so usually when we talk about array data, that's what we really mean. Okay, so now that's what you need to minimize. This is, of course, so we are in the data space here. So if you let D1, D2 be 2 data, then Of course, this is the norm induced by an inner product, which I write it here. So this is integral over time, sum over the sources and receivers of d1 of t xr xs, conjugate d2 t xr xs. So that's the inner product that we consider. So the bar will always mean conjugate for me. Okay? And so now if you write the optimality condition, you know, so the minimizer satisfies this equation. Okay? And so now let's look at this equation. First of all, let us look at the right-hand side. So you have, this is the adjoint operator. So I guess there's a lot of repetition. So what is this adjoint operator? So formally what you write, so you have, okay, so you have df acting on the reflectivity, and then here you have, I'm going to call that whole thing d minus f of v. I'm going to call it d1, okay, just to save space. So formally you define the adjoint in this way. Okay, so now this is an inner product that lives in the space of reflectivities. Okay, so that is integral over y of rho of y, and then you have, let's put conjugate, and then you have d f star d1 at y. Okay, and so now by using the expression of df, just substituting is very easy to find what is the expression of the adjoint operator. So let me write it down. So the adjoint operator is, yeah, actually, just to be consistent with the slides, let me call this, instead of d1, I'm going to call it p. So p is now really what I measure. Okay? So the adjoint operator is df star v acting on the data that we measure. This is a function of y, is equal to integral over the frequencies of the complex conjugate of the pulse. You have the factor omega over v squared, and then you have the sum over the sources and receivers of what you measure and then you have the Green's functions. So these are the Green's functions of the Helmholtz equation, the outgoing Green's functions of the Helmholtz equation. Complex conjugate. So that's the definition of the adjoint operator. Okay? So now this adjoint, and that's for the scattering problem. Okay? For the source problem, it's slightly simpler. So for the source problem, you are going to have integral over the frequencies, the complex conjugate of the pulse. You only have receivers now. And then you have the Green's function. Okay? Oh, complex conjugate. So this is for the source problem. Okay. So now let's look a little bit at this expression. So for the source problem, that's more intuitive. So when you look at this expression, you see that this expression is basically the famous time reversal function. So that has been discussed so much here. Okay. So except for this guy here, so if we didn't have this guy here, what would this expression mean? So what would you really do? This really models the experiment that goes like this. You have the source here at y, okay? Then, you have the source at y. This at y star, I think I called it. This emits a pulse. That's going to propagate in the medium. Here at the array, you capture that signal. You time reverse it, and then you send it back, and you observe the signal at points y. Okay, so that's exactly what this models. Okay, so that's the time reversal experiment, and of course now everybody talks about that. And in fact, I will have to say that this is maybe, so this time reversal experiment gained a lot of attention after the experiments that were done in France by Matthias Fink, because he showed that this time reversal this time reversal process has remarkable properties if you do this in a highly scattering medium. So in particular, it gives extremely good focus, much better than if we didn't have the scattering medium. So that created sort of a frenzy of research, and now everybody is doing time reversal one way or another. Okay, so this is the time reversal. And here for the scattering problem, that's what I'm saying. So I say, look, if you look really at the right-hand side here in this in these equations, you find that this is really not so different than what we call the time reversal function, which is the function. So in the scattering case, it looks like that. So it just takes the data and it back propagates it in the medium to the point y where you form the image. Okay? And so now there are two things that we have to discuss. Now the first thing is, so this time reversal function, if you knew the medium in great detail, well, then that will be, you could use that as an imaging function. So now the question is, will that work? Well, the answer is yes, it will work, and it will work actually remarkably even if you have scattering media, which is what I'm talking about here. All right, so now what's the relation between this and this again, as I described here? So you see that there are very small differences between this and this adjoint operator. So what we are missing here? Well, we are missing this factor, omega over v squared, and we are missing this factor, which is the complex conjugate of the pulse. So the question is, are these factors important or not? Well, so usually, in practice, they are not. So omega over v squared is usually not so important, especially in the case where you have a bandwidth which is large, but still the bandwidth is much smaller than the central frequency. Okay? So this is very much the case in most applications. So certainly in radar, for example. So okay, so for example in what is called X-band radar, the central frequency is of the order gigahertz, and the bandwidth is of the order at most hundreds of megahertz, so it's much more. Okay, so that factor is not going to make much difference. Now what about this one? What about this factor? Does that make a difference? And the answer is, this may make a difference depending on what you send from the source. So in our case, because we are assuming that the source sends a pulse, then this factor doesn't make a big difference. When will this factor make a difference? So this makes a huge difference actually if the source emits sort of long signals, what is called chirped signals. So why would that be important? So what is a chirp? Well, so remember that I'm talking about signals like this, and an example of a chirp signal, so there are various versions of chirps, is a signal that looks like this. So this chi is supposed to be a window of support 1. So Tc here is the time scale of the chirp, and that's supposed to be long. And this parameter sigma here is what is called a frequency modulation parameter. Okay, so why would one want to do this? So the reason is the following. So for example, in radar, what one does, right? So you have an airplane, and then you send from the airplane a signal down, and then that's going to scatter, and you are going to record back, right? So what happens is that, of course, the imaging scene that you want to find is going to be noisy. Okay, so what one usually wants is to have a signal that is strong, right? So you are looking for strong signals. Now, so it turns out that it's impossible to send that too much energy in a short pulse, but it is possible to pack the energy into a much longer signal. Okay, so that's the reason why one uses these pulses, so these chirps. So you have now this Tc is long. Okay, so you send a long signal. Okay, well, if you send a long signal, that's not very good for imaging. And then this multiplication with this F conjugate is what is known as pulse compression. So let me explain to you how that goes. So if you do the Fourier transform of this chirp signal, you are going to find, after trivial calculations, okay, that it's approximately equivalent. The approximation is under the assumption that sigma Tc squared is much bigger than 1. So that's the assumption in the approximation. You are going to find that this is given by this. Okay, so this is how the Fourier transform looks like. Now, so in your data P, the data that you measure here, for example, there is a pulse, right? Because the source emitted a pulse, so there is a factor F omega here. Now, when you multiply that with the complex conjugate, you are really going to deal with the absolute value squared of the pulse. Now, the absolute value squared of the pulse is just P over sigma chi of omega minus omega 0 over sigma Tc. So this is a function, because this is a function, the function chi, this window chi, has support 1. So this is a function that has support in the frequency domain of order sigma Tc. So in other words, the bandwidth, the apparent bandwidth of this is like sigma Tc, right? Now, if you take this back in the time domain, you are going to get a pulse with time support, which is like 1 over sigma Tc, okay? But this is much smaller than Tc. So in other words, what you have done is you emitted a long pulse over a time window Tc, okay? And then by multiplying with this F conjugate, what you have done is you have compressed the pulse to a much shorter time, which is determined by 1 over the bandwidth. Okay? So that's what is known as pulse compression. So that factor is important, but only in that situation. Okay. So, all right, so then now we can basically say that really in our context, this time reversal function is basically the same as the right-hand side. And then now the question is, what about this guy? So what we are going to do is we are going to say, okay, well, we are going to look at this right-hand side of this equation, and that is going to give us a qualitative approximation of the reflectivity. Okay, so that, you know, means, but what about this? So what about this operator, df star df? That's the normal operator. Okay, so usually in practice, it used to be that one would ignore this operator. You know, they would just say, okay, you think of it as the identity. Why is that the case? So there is a lot of analysis that has been done in the case where this v is a smooth function, and there are results that say, for example, that this is a pseudo-differential operator, and as such, it does really nothing to the singularities of this rho, which is what we want to find. And in that sense, you can neglect it. Now, of course, in practice, that's never going to be the case, so that result amounts to, again, assuming infinite bandwidth and all that, and we never have that. So it is known in practice now, so people have started to work on inverting this operator. There is very nice work that is done in that context. And, well, if you want to think of time reversal, this df star df is the famed time reversal operator, so that was just described by Andreas this morning. Okay, so this is the time reversal function, and so this was a very, very long introduction to what I want to talk about. So in the next lecture, I will actually start talking about what I want to do. Okay, so.